Welcome back everybody to Environmental Science 101. Here we finally get to talk about our atmosphere. Was the atmosphere there from the very beginning of the Earth? If we go all the way back to the magma ocean? No. But it forms over time and was most likely there in its present form following the injection of all that oxygen. If you remember that slide where we talk about oxygen into the atmosphere. Okay, awesome. Let's get into it. So this is the atmosphere that we know and love. Hopefully love. Try living without it. Okay. We don't need to worry about these terms, and we don't necessarily need to worry about these heights, but just to put it into context, right? So 0 to 12 or 18 kilometers, right? That's from the ground all the way up to here, is considered the lower stage of the atmosphere. For reference, 12 kilometers is about going to be the height of Mount Everest, right? Pretty cold at the top. Moving up into the stratosphere, mesosphere, thermosphere, and exosphere, we have some things that we know and love, right? So meteors tend to ignite at about this point. So weather balloons up into the stratosphere and mesosphere. At this point, it is only the aurora borealis at this time of day and this time of year. And then finally, we have spaceships and orbiting satellites all the way out from 800 to 3,000 kilometers or even further. Some of the satellites are much further away than others. Awesome. We notice something else about this, right? What is happening to the temperature? So the temperature is actually going to be warmest, right, when we are lower down, closer to the surface of our warm Earth. And as we go up, right, on top of the mountain, it cools off. But we also might remember that warm air rises. So warm air has a lower density than colder air, right? The molecules are moving around more, and so its density is less as a result. And so we have this kind of flipped, right? So the warm air, right, is going to be the stuff closer to the surface, which is going to want to rise up, and colder air is going to want to come down. And if you're thinking to yourself, oh, this is maybe something that drives weather, then you would be exactly right. Yeah. We need to talk about the composition of the atmosphere, not just its structure, but what it is made out of. So to put this in context, our whole universe, mostly hydrogen, helium. We're not really interested in that, but that's what it mostly is. Earth's crust is going to be made out of all these other denser, heavier stuff. As a fun fact, rocks are mostly oxygen, some silicon, and then all these other elements. And then this final one is what we're really talking about here, right, which is our atmosphere. So it's going to be about 80% nitrogen. This is going to be like N2 gas. It's inert. It doesn't react with stuff. It doesn't mess with people. For better or for worse, it's just a gas that's sitting there being itself, but it doesn't react. We got oxygen, which surely does react and hasn't always been there, as we have now learned. And then we've got everything else smushed together here in about a percentage. Just something that is interesting about this graph, right? We notice that carbon dioxide is here at 0.038. What that tells you is that this graph is outdated because carbon dioxide is higher now than whenever they made it, because that one is continuously going up. So it really should be something like 0.04243, which is pretty significantly different on a chart like this. Interesting. Okay, we remember, right, our spinning disk. So we have our interstellar cloud of gas and dust, interstellar nebula, and over time, right, the stuff attracts the other stuff due to gravity. It condenses down. Everything cancels out except the rotational component of motion. Our sun ignites. The planets begin to suck up everything that is near them and get rid of it. And now we have our spinning solar system. And we knew this was going to come back. And how does it come back? Well, our Earth is still doing this, right? It is this leftover momentum from the formation of the solar system, right? So we have our Earth orbiting, and it is also spinning counterclockwise on its own axis. And this is what this is going to look like, right? So counterclockwise from our chosen orientation here. Does it rotate, right, along the same axis that we would expect relative to how it goes around the sun? No, it is slightly tilted, right? So we've got our north and south pole, geographic north and south. We have a slight tilt, right? In other words, it is not perfectly in line in terms of how it rotates with the rest of our solar system. We have our equator, right, which we can draw as our sort of fattest line around the Earth here. Yes, our equator, right, going to be our largest line we could draw that is perpendicular to our north-south axis. Okay, so we are rotating counterclockwise around this axis. We have our equator, which is perpendicular to it. In combination, right, rotating around the sun, rotating around its own axis, we can explain our seasons, which is going to be extremely relevant ecologically. So at certain times of year, the Earth is going to be tilted right towards, or we should say the northern hemisphere is going to be tilted towards the sun, receive disproportionately more sunlight and radiation. Other times of year, the southern hemisphere is going to be primarily right tilted towards the sun and receive a greater proportion of its incoming radiation. And this is why we have our seasons change and why seasons are going to be opposite in the northern and southern hemispheres. And then other times in between, we would have our spring and fall, where we're neither getting the most nor the least incoming solar radiation. Awesome. We also have, as a consequence of Earth's rotation and the factors we're talking about, like sunlight coming in and striking the Earth, right, primarily about here, is that we have global atmospheric circulation patterns as a result, right? So most of the sunlight, broadly speaking, is going to come in and hit us at the equator, and it's going to warm up the air at the equator. That air is going to rise up. It is going to move away from the equator, which is literally the only way it can move in, right? And it is going to come back down after cooling off and dropping all of its moisture as dry, cool air here at about 30 degrees north latitude. We don't really need to worry about latitude. We don't need to worry about the terms, but the overall sense of it is important. We have these complementary cells, right? So cold, dry air is coming down here. Our complementary cell, as a result, right, where does that air go now that it's being warmed up closer to the surface? It has no direction to go except away from this point, right? Either traveling north, warming up, and then forming another cell, or traveling south back to the equator, only to go through this again. Our polar cells are going to be a bit different. These are, in fact, so cold that the air cannot hold on to any moisture, and so you get no precipitation in this place, right? As a result of these cells, right? So radiation comes in, warms the air here, right? It comes up, it starts to drop all of its moisture. By the time it has moved away from the equator, it is nice and cold and dry. It is not able to hold on to moisture at all. Then when it comes back down as cold, dry air, is this area here going to get very much rain? The answer is no, right? The same thing happens in our southern hemisphere. So now we have some sense maybe of why we might get these areas called deserts, which get very little rain, right? And why they might be clustered around these lines, which we will see again shortly. We also have an idea of why our polar regions don't get very much rain. There's one last part to this that I want to talk about very quickly, right? So we mentioned how our Earth is rotating counterclockwise, right? And we can see the result of that here. So our Earth is rotating counterclockwise, right? And if you can imagine that happening, you can see why winds at the equator are going to blow to the west, the so-called westerlies. Okay, so let's hang on to those, right? We mentioned how places where cold, dry air comes back down, we have deserts, and here we can see the world's deserts. You might notice, right, that it occurs in these stripes, right? So if our equator is about here, then at these certain latitudes, right, north or south, especially this one in Australia, you get deserts systematically. These are going to be our subtropical deserts. This overall is fairly generous as far as what it includes as being a subtropical desert, but you will notice that it includes our Sonoran Desert, which is so dry in part due to this factor, alongside the fact that we have some sort of a rain shadow effect. Essentially, there are mountains that block precipitation from coming in off the ocean, right? So combined with this global atmospheric circulation and our rain shadow effect and the fact that this is cold water here to begin with, and here we get our Sonoran Desert. Awesome. We can also look at precipitation patterns worldwide and connect them to these global atmospheric circulation patterns, right? So here we have our amount of circulation. This, I believe, is in centimeters per year. I'll add a note if I end up being wrong about that. We notice it is extremely, right, going to be clustered near our equator with these giant dry spots, right, at about 30 degrees south latitude, including Australia here, about 30 degrees north latitude, including our Sahara Desert. So we can see how those atmospheric circulation patterns directly control precipitation and, as a result, biodiversity, right? It's going to be the highest here in the middle where it is warm and also wet. And in fact, if we were to look at a biodiversity heat map, it would look extremely similar to what we have right now, except with a little bit more of a hotspot here in our Amazon. Okay, that is going to complete our discussion of global atmospheric circulation and the ways that we connect that concept to our own Sonoran Desert and to biodiversity overall, as well as other factors in climate. Next, we will move to the human element and talk about air pollution, connecting all of what we talked about so far to the stuff that we breathe in. So stick around.